We continue with this session. We now have another speaker, which is Pasquale Serpico from the NC laboratories. And he will continue with this discussion about dark matter, and in particular he will review the main cosmological and astrophysical evidence for dark matter, and he will give us some more information about searches performed at the colliders and at the different experiments. So as Antonio said before, it's a great pleasure for us to have today the speakers. These seminars today anticipate a workshop that will start tomorrow, that we, people which are working on the particle level, elementary particle field experiments, will join. And okay, tomorrow we will have this workshop which is dedicated to experts, but I think that also for people which are not strictly involved in this kind of searches, is a very good opportunity to learn more about these hot topics, and dark matter, of course, is one of these. So I will give Pasquale.
Thank you. Thank you for the invitation. So the topic, you see it repeated on the title of my first slide. So I'll try to cover from cosmological evidence of dark matter to searches at colliders. So this is a quick preview. The outline of my talk is non-proportional in time among these 6 items. Namely, I will spend maybe 30% of my time on this item number 1. Who ordered dark matter? What do we know about dark matter and how? I think that some of these might be useful to those of you who asked themselves, as I did, questions about are we sure it's really there? How do we know it? Why it's non-baryonic, and so on. Then I'll specify what we mean by discovering dark matter, because if you talk to most astrophysicists, they would say, okay, it's already discovered, so what are you looking for, really? Here, the search strategies actually have an interplay with collider searches. Then I will illustrate one strategy for indirect dark matter detection, the gamma ray case. I cannot go into details of all of them. And instead of taking a top-down approach, I will describe an explicit example of how current astroparticle physicists work, in the sense that they use possible claim of excesses, say, in the astroparticle sector, cross-checking it with constraints from collider physics, or the other way around. And then maybe, if I have time, I will revisit the link between particle physics and dark matter, and I will spend some time to thoughts on less conventional paths to dark matter searches. Hopefully, I will be pedagogic enough that all of the audience can follow. If anything, the technical part probably will be here. Okay, so at the beginning, when dark matter entered the scene, it has nothing to do with cosmology. It's a purely empirical evidence, and it was discovered for the first time by Zwicky in the 30s, studying a specific cluster of galaxies first time, the Coma cluster. Here you see a modern picture, roughly 1,000 of galaxies in a typical size of a megaparsec. So roughly, the radius is roughly of the order of, say, 100 times the radius of the visible radius of our galaxy. And Fritz Zwicky was a very creative astrophysicist, and actually also an outlier in his field, despite the fact that you see in Barna here the acknowledgement that he discovered neutron stars and the dark matter in the universe. He was not always well appreciated by his colleagues. You see him in a typical expression. And we remember him for 2 important discoveries. One is that astronomers are spherical bastards. No matter how you look at them, they are just bastards. And this is because he had hard time getting some of his discoveries actually acknowledged by the community. And the second, and perhaps most important for today, he found a mismatch between the mass inferred for this cluster using 2 different techniques. One is quite traditional in astrophysics, namely you basically measure the light, the amount of light you see, and based on a expected light to mass ratio, convert into the total visible light of the cluster. And the other one was quite innovative, actually, for the time. he used a mechanical theorem, the virial theorem, to infer kinematically from the movement of the galaxy in the cluster what their mass should be. In fact, the virial theorem, which applies to a system of n particles bound by conservative forces, tells you a relation between the average kinetic and potential energy of your system. And actually, from this relation, it could infer the total mass of your system in terms of observable quantities, namely the Doppler shift in galactic spectra that determine the root mean square, if you wish, of the typical dispersion velocity of your system, and geometrically the size of your cluster, and basically found a mismatch of a factor 400, which was big even for astrophysics, and even for the 30s it was too big to enter into the error bars. And so this is the first time dark matter makes its appearance in astrophysics. Of course, here he didn't say anything about what this dark matter is. Could be perfectly some unaccounted form of baryonic stuff. Actually, even today, people do study the same kind of clusters. Again, this is a modern X-ray picture of the same cluster, the coma cluster, to infer something more precise about dark matter. In fact, the mass, the baryonic mass of galaxy cluster is dominated by gas. And since these clusters have a huge mass, actually their potential wells, gravitational potential wells, are quite deep, so that basically the temperature of the gas virialized in these depths is quite high, and it shines in the X-rays. Okay, so through X-ray maps, you can use the total intensity to tell you about the total amount of baryonic matter, and the temperature, or if you wish, the spectrum, combined with some hydrostatic equilibrium to tell you about the pressure or the profile, the gradient in these clusters. And again, we confirm qualitatively what Zwicky saw, although now it's more like a factor 7 more mass than what is contained in the cluster, what needs to be explained. And one reason Zwicky was wrong is that actually he didn't know that clusters are dominated by the gas. The baryonic amount of matter in a cluster is actually made mostly of gas, not of stars. Okay. There are even more spectacular proofs coming from clusters. This is a picture from Hubble Space Telescope, and you see all these arclets, which are basically distorted shapes of galaxies caused by a huge amount of mass on the line of sight. This is gravitational lensing, and from these maps you can try to reconstruct the kind of optics that you need in order to determine this deformation pattern. And this is a typical reconstruction that you get. You see a density map which presents some spikes corresponding to the galaxies that you see, but you need, in order to fit the data, you need to assume that there is some continuous smooth distribution of extra matter, which is what we call dark matter, and actually dominates the total potential. Okay? More spectacular proofs are provided by segregation. Sometimes clusters collide, and you can map the distribution of matter once again through lensing, gravitational lensing, and you can map the presence of gas, baryonic gas, through the X-ray emission. This is shocked hot gas, and this is what happens here. This is the famous bullet cluster. Here you have the shocked fronts of gas. Here you have the mass dominating the gravitational lensing potential reconstructed from the deformation pattern of the galaxies behind, and you see that they are segregated. So whatever causes gravity passes through each other, does not behave like gas, which is shocked behind and stays behind. So most of the mass is not in the collisional gas. Okay? And if the Newton's law, for example, were different, you should expect that whatever the alteration is, the potential should still be centered on this shocked gas. Okay? And you may have heard also about the fact that if you map the rotation curves of stars in a galaxy, notably in spiral galaxy, you expect the rotation curve, just by combining the centripetal acceleration force with Newton's law, you end up with a square of the rotation velocity, which goes as g times the mass enclosed till radius r over r, and this should be constant, where this r is the integrated mass. Instead, you see, sorry, what you see, this is what you see, and what you should actually expect if most of the mass is concentrated near the center of the galaxy is a decrease of 1 over r, which is, by the way, what you see in the solar system, okay, where the sun dominates the total mass. So actually, you can fit this discrepancy by making the hypothesis that there is a huge halo of matter in galaxies, which far away from the central region of the galaxy falls like 1 over r square. Okay. Now, this is quite important historically. Vera Rubin and collaborators, in particular in the 70s and 80s, convinced many people this was robust, although there is some astrophysical model dependence here. But historically, this convinced many people, in particular in particle physics, that there was a problem to be taken care of. Okay, and still, it's quite important for observations like this direct detection in underground experiments you heard about before, because it depends. The rate of events is depending, for instance, on the local density of dark matter, and how you determine the local density around us in the solar system of dark matter depends on these kinematical studies. Okay. However, what is more important for particle physics is the dark matter evidence that you have a very large scales. Large scales here means cosmological size, gigaparsec scale. Okay, in order to explain, at least qualitatively, why this is important and what's all about, let me start with some basic notion of cosmology. So modern cosmology is based on a few pillars, observational ones. The first one is almost 1 century old. In particular, is the observation by Hubble that galaxies sufficiently far away from us recede with a velocity which is proportional to their distance. This is one of these original diagrams. Another one is that the universe is permeated by an almost perfect black body radiation, which is in the microwave wavelengths, corresponding to a temperature of slightly less than 3 Kelvin. Actually, by almost perfect, I mean perfect to 1 part in 10 to the 5 or so. And the fact that hills of light elements, notably deuterium and helium isotopes, is way larger than what you would expect from any conceivable mechanism of stellar synthesis. Okay, so this is also an evidence of a early hot epoch in the history of the universe. Now, based on these observations, cosmologists have built a standard cosmological model which uses general relativity, namely this is a metric theory of gravitation plus specific form of Einstein equations. The cosmological principle, the fact that we are not special place in the universe, on large scales around us, the universe should be homogeneous and isotropic. And then you plug in some standard physics, particle physics, nuclear physics, atomic physics, plasma physics, and so on and so forth, in a regime which is very well known. And then you ask yourself, what's, for instance, the evolution in time of the composition of the universe? One of the basic inputs for this program to be achieved is to specify at some time what are the ingredients that enter in the universe. So you have seen these pie charts before. For instance, the current pie chart looks roughly like that. You have 70% or more of dark energy, 23% or more of dark matter, and the rest is being constituted by baryons, normal atoms. And just to, since we will use some Hubble rate and some basic correspondence between these and particle physics time scale, let me just justify, for those of you who have no notions of general relativity, one key equation. Namely, consider a toy model. Consider a model where you have a sphere of dust particles, and you look at the dynamics of a dust particle in this homogeneous sphere, which is at a distance a from the center of this sphere. So the Newton's equation writes simply as I did here in this passage, where the mass is the mass enclosed by the sphere up to the distance a, and by integration, this is equivalent to this form, okay, for the scale factor of this dust sphere, which depends on an integration constant which needs to be determined. And this is nothing that the Hubble law h square is the square of the Hubble expansion rate, which depends in general on time, and this is dynamically linked to the density of the stuff which is in the universe, and in principle to a constant which in general relativity becomes linked to the geometry of the universe, in particular if the space part of the universe is Euclidean, this is 0. And the additional equation that you need to do basic cosmology is basically the conservation of energy. So in general relativistic cosmology, the expansion of the universe is ruled by the energy content, and the conservation of energy is generalized to include also a pressure term. But basically, this is the conservation of energy. So once you specify the equation of state of your universe, which means the matter or radiation content of your universe, you have specified your model. And usually, you express the abundances in terms of these omega factors, which are essentially the abundances of different species normalized to a critical value, which is derived from this equation at current time. Okay, don't bother about details. That this is just to set some notation fixed for the rest. So one of the basic implications of these equations is that if you look at how the evolution goes for a universe where you only have matter, what does it mean matter for a cosmologist? Is something where you remember the equation of state of gases, right? PV equal nRT. Well, T is the energy in kinetic stuff is way, way, way below than the rest mass energy of your particles. So basically it's pressureless stuff, which implies that the evolution of the density goes as the scale factor to the -3. And if you have radiation like photons, well, the evolution of the density in the universe goes as a to the -4, so it's faster, which also means, well, you can explain heuristically what happens if you have just particles on a grid and this grid expands. Well, the density of particles in your grid scales as 1 over the volume. That's quite obvious. But if you have radiation, you have a further factor because the density of the photons in a given volume also gets stretched because the wavelength of the photon is diluted. But this also implies that if you go back in time, since there is some radiation right now around us and there is some matter, if you go back in time, at some point, since this grows faster than this one, at some point, the energy budget of the universe will be dominated by radiation. So back then, the universe was much hotter, okay? And basically, in a Cosmology 101 class, you can tell the audience immediately that the history of the universe is going to be a sort of history of departures from equilibria, okay, of different sorts. And in order to understand when this happens, you just need to compare the rate of the process under consideration with the Hubble expansion rate. You saw just an example before when Tomer was computing the freeze out of WIMP dark matter. Okay, so for instance, this simple atomic physics reaction, the recombination of electrons and protons to form neutral hydrogen, well, it had to happen sometimes in the past when the temperature of this hot bath was of the order of electron volt. And in fact, this is the process which sets the release of photons and basically form the cosmic microwave background that we see today. Now, I did all this just to explain why this picture that you might have seen, this is the temperature fluctuation in the cosmic microwave background, is basically a picture of dark matter. This is one of the best proofs we have that dark matter should be there, and it's relevant at cosmological scale. Why it is so? Because these fluctuations are at the level of 10 to the -5. And basic physics, this one tells you when this was formed, okay? Now, you just take gravity, you evolve forward in time, and you ask yourself how long it takes for these fluctuations to collapse into nonlinear structures like stars. It turns out that if baryonic gas is all there is around us, it will take forever, much longer than the age of the universe. So the only explanation that we have for the stuff around us, compatible with this picture, is that in reality, the potential wells that are at the origin of the structure around us are much deeper than what you see. Okay? And for those of you who like some mathematics, this is a slightly more formal way to explain the same thing. Namely, you can describe the density contrast, the density of your gas with respect to the average -1. You decompose in Fourier modes. Why you do so? Because in linear theory, these are independent. Each mode, each scale evolve independently. And then you ask yourself an atomic physics problem. You have photons, you have atoms, nuclei and electrons, and you have possibly some component of dark matter. How does these modes evolve in time? And this is the picture. So basically, these modes, well, here you don't see anything because these modes are not causally connected. But at some epoch, for a given scale, these modes behave like sound waves in a gas. And these are the oscillations that you see here. Okay, red is photons and green is baryons, atoms. And you see that by the end of this oscillatory period, this end is set by the recombination mechanism, the recombination phenomenon I was just introducing before. Well, what would happen is that the density contrast is very low, is of the order of 10 to the minus 1 to 1 in the baryon to photon system at this wavelength. But since we make the hypothesis that there is some cold dark matter, in reality, the density contrast in the cold dark matter is much, much bigger, like 10 times, 100 times, 1,000 times bigger. And this is why baryons immediately collapse into these structures and can grow nonlinear. So at the end of the day, today, you have density contrasts which are deeply in the nonlinear regimes. Okay? And if there was no dark matter around, you can compute what the structures at large scale should look like. Okay? In particular, you can compute the power spectrum, which is the variance of the density contrast I just introduced before. As a function of the scale, it would look like that, like the red curve. You would see exactly these acoustic peaks, and these are the data. These are data coming from surveys. So you would fall short by a factor of 100 or thousands of the data, and the shape would look quite different. Okay? So it's not enough to say the gravity at large scales is, say, much stronger than what we think, because the result would not match the observations. Okay? This is a very, very powerful constraint on any modified gravity model you may think of. And in fact, the fact that we understand what's going on and we can measure even the ratio of baryon to dark matter comes from the fact that we have measured these little wiggles here, which are the little brothers of these huge wiggles here, due to the fact that there are some baryons. So there are some sound waves. Okay, so not only we see the dominant effect of dark matter, we even see the subdominant effect of ordinary matter. Okay, and the same you can do with CMB. So I'll skip that. The same you can do with CMB, with the cosmic microwave background, and the same comes from the Big Bang nucleosynthesis. Okay, so we have concordant information coming from different epochs in the history of the universe. What do they tell us? All this cosmological evidence, and why the cosmological evidence is important for particle physics. It's essentially based on exact solution or linear perturbation theory of known physics. Okay, this is a very important point. There is nothing exotic here. It's gravity, atomic physics mostly. Okay, this is credible and robust. It suggests that you need additional species rather than modifying gravity. And it also tells us that most of what you need is non-baryonic. Okay? It's not made of planets or stars that are too dim to be detected or anything like that. And if you combine this information, there is nothing in the standard model of particle physics that can explain it. Okay? The only things that come close to it are neutrinos. But actually they fail. And they fail for some subtle reasons that if you are curious about, you can ask me later on. So this implies that dark matter requires new physics beyond the theories that we know today. And since there are only a handful indications of this, that's what Tomer told us, right? Baryogenesis, possibly inflation, and so on. This is why particle physicists are so excited about this dark matter. Okay. However, there is a big, big problem that gravity is universal. So astrophysicists may say, okay, you have already discovered dark matter. What else do you want to do? Well, unfortunately, we want to identify what dark matter is. And we cannot identify what dark matter is only with gravitational probes. Okay, because everything gravitates. So you need to rediscover it with some other probe. And that's where the model dependence comes in. In addition, cosmology and astrophysics also tell us a few basic facts about what dark matter should do. In particular, dark matter is stable or at least very long-lived on cosmological timescale. We are talking about tens of billions of years. Dark matter, well, it's dark and dissipationless. It must be collisionless to a large extent. It means that it's much less collisional than baryonic gas. Okay? Otherwise, we couldn't have seen this big cluster passing through each other with that pattern. Dark matter is also smoothly distributed. You saw an example in this cluster of galaxies. You don't need really, clumps. You need something smooth. Dark matter behaves as a classical fluid at astrophysical scales. And also, it's not hot. It means that it has a non-relativistic velocity distribution. I have no time to describe any of these points, but please ask me if you are curious about any of them. So here is where the traditional link with particle physics kicks in. If now you have a strong prior, and we just heard why we have a strong prior for TeV-scale physics with electroweak scale couplings, well, for instance, due to the hierarchy problem, the naturalness problem, precision electroweak data, in particular already at the LAP era, suggests that three-level couplings like standard model, BSM, where BSM is whatever new physics you have, should not be really allowed. Okay? So you don't want to have this if this particle is light enough and this coupling is sizable enough. So this you can live with often. One straightforward solution to do that is to impose some symmetry so that a pair production of this whatever new physics is allowed, but a single stuff is not. And this has the benefit of, okay, from the theoretical point of view, this might come from some relic of a symmetry which is more meaningful in the ultraviolet regime. But in many theories of the standard beyond standard model at electroweak scale, you have something similar. In SUSY, you have R parity. In extra-dimensional models, you may have Kaluza-Klein parity, and so on. So new particles should only appear in pairs. And this automatically makes the lightest particle under this new extension of the standard model stable. Okay? It has also other benefits. In the case, for instance, of SUSY, this was not introduced for having a dark matter candidate. It was introduced not to violate the proton stability bounds. Okay? Fortunately for us, the protons do not decay too quickly so that we are around. And in order to prevent the protons to decaying from too quickly, this was imposed in supersymmetric models. By products, you also have a dark matter candidate. So, bottom line, cosmology tells us that the early universe was a hot plasma, a soup in which all thermodynamically possible particles that could be produced kinematically were produced, and this paradigm has been tested up to temperature of MeV scale, okay? Because we have a good match between the pattern of light elements that have been measured and what has been computed. Now, what happens if we extrapolate this back in the past, adding this new stable particle? Well, that's exactly the WIMP miracle Tomer was talking about. I won't repeat it, but it will mean that we have an extra relic from the early universe. Just we have other relics like neutrinos or photons from the early universe. And this extra relic abundance, in terms of the critical density, scales inversely proportional to the cross-section of annihilation of this particle into standard model states, sorry. And the big surprise is that this comes out to be of the right value for electroweak coupled particles of electroweak scale mass. Okay? So, in summary, the stability of this particle results from the same discrete parity symmetry that we needed for other reasons. It matches the old theoretical prior for beyond standard model physics at the weak scale, and also lead to a number of phenomenological consequences. So this is the theoretical motivation for the baseline model search for at colliders, direct detection, or indirect detection. Now, first caveat, this is not the generic dark matter paradigm. It's a WIMP, weakly interacting massive particle paradigm. And basically, we don't know what kind of new physics enters the interaction of these new particles with standard model ones. But we know that if the picture I described previously is correct, and there is some some new interaction that mediates their annihilation into the standard model, well, not only it can go on in the early universe, it can also go on in the present-day universe in potential wells which are deep enough that they collect enough dark matter, for instance. Also, you can try to produce, to look for the recoils against nuclei. So here you have a nucleus, and through this new interaction, this can recoil against this nucleus. Or you can try to produce from standard model particles dark matter particles. Okay, so in the case of indirect detection, where you look for the annihilation of these particles into standard model final states, you see that generically you expect many standard model final states to appear, which means that you can expect correlations between different channels, like for instance positrons, antiprotons, gamma rays, neutrinos, and so on. So the program is that to demonstrate that the particle physics nature of the astrophysical stuff that you see out there can be matched by whatever you produce at a collider, like the LHC, and possibly find consistency relation. For instance, checking that the couplings needed in one observable are coherent with the couplings that you need in another observables. Okay, so that's the whole basic logic of the program, search program that is going on since 3 decades maybe. Now, what are the WIMP-related observables that we expect at colliders? The only thing that we know for sure is that, for sure in this paradigm, of course, is that the standard model should be extended by at least a new neutral and not colored particle, massive state, which is in general the lightest state of a new sector, which has many, many states available. This is an example of pre-LHC spectrum of new particles associated to a specific supersymmetric scenario. And you see that besides the standard model like Higgs, you have many, many, many particles. Okay? Unfortunately, what is the most effective strategy in searching for dark matter colliders depends on the rest of the spectrum. Depends in reality on the masses and couplings of all the other particles. So it's intrinsically model dependent what you can look for at LHC. However, we haven't found dozens of new particles at LHC. Okay? So there are some sort of simplified framework in which you can look for dark matter of WIMP type at LHC. The first possibility is that these heavier states, heavier than the dark matter candidate, are not kinematically accessible. So, are kinematically accessible. I treat first this one. Unfortunately, a realistic BSM model might contain lots of states. Okay? In the SUSY model, you have at least more than twice the degrees of freedom than in the standard model, and you have more than 100 free parameters. Okay? So you cannot really explore the whole parameter space. So what you do to deal with that traditionally is to start with simplifying the model. For instance, you assume that all fermions share the same mass scale at some energy, that all scalars do the same. Then you pick some benchmark reference models which you think are representative of different conditions, different regimes, okay, hoping that they are representative. And then what you do, you look for the constraints acting on the states which are more easily accessible, for instance, colored states. And then you use theoretical relations to see what these imply for the so-called dark matter candidate in your theory. And this kind of strategy is going on for decades. So you might have seen, for those of you who are particle physicists, I'm sure you have seen constraints on dark matter in a plane where you have the common fermion scale, the common scalar mass scale in the constrained MSSM with a band which is motivated by cosmology. Well, it's not that we think that these kind of studies are closer to the truth. The only hope is that these are realistic enough that they teach us something generic. There is an alternative strategy, which is that you have no heavier states kinematically accessible at the LHC. Okay? The only state that you may hope to produce at the LHC is the dark matter candidate. Now we have a problem, because if we just reverse the diagram I just showed before, you have a process like standard model into dark matter, and then you're screwed, because this is by definition invisible at the LHC. So you cannot look for dark matter with this process. So the next best choice is to look for a process where standard model goes into dark matter, plus something visible, where this something visible might be a photon, a gauge, massive gauge boson, or jets. And this is unavoidably present at some level. Why? Because at least the initial state couples with them. Okay? So you look for some mono stuff recoiling against a lot of missing energy. To compute the rates for these signatures, what you do, if you have a complete theory, you can integrate out the heavier states, okay, and construct an effective field theory, which is a complicated way of saying that you do something similar to what Fermi did almost a century ago, when he replaced whatever propagator of new physics entering the decay, for instance, of the neutron, with some effective contact interaction, which we know today that if you zoom out and look into detail, will describe the exchange of massive gauge bosons. Okay? So the fact that these mediator particles, here the W, is heavy, is what translates phenomenologically into the fact that weak interactions are weak. Okay? So you may hope to redo the trick for dark matter interactions through a mediator scale. What happens if you do? Well, actually, this is not an idea I just had. This is a strategy that has been applied to LHC data since it started. You see here some indication of even early run 1 data. And this is remarkable because you can compare now the reach of LHC in constraining these effective field theory models, which can go even beyond the reach of direct detection techniques and exclude cross-section for very light particles. So it seems almost too good to be true. And in fact, it is too good to be true, in the sense that the effective field theory strategy is running out of steam. Why? Because the LHC now typically produces processes where the exchange momentum is high enough that it can resolve what goes on into this blob. Okay? So these effective field theories are not a good tool anymore, and so we should go to something different. This something different is a sort of compromise approach, which is sometimes called simplified models. What are these models? These are models where you forget about all the heavy states, but for the dark matter and the leading mediator of dark matter interactions with the standard model. Okay, so you see these are compromised in the sense that you do not really take into account the whole complexity of your model. You do not forget completely about it, but you include just a little bit. Okay, and there are some rules how you construct these these simplified approaches. But the typical parameters that you have in this theory are the mass of your dark matter candidate, are the mass of the mediator, the particle exchanged with the standard model, and the coupling with the standard model of the mediator and of dark matter with your mediator. So now this is a sufficiently well-defined framework in which we can compute things meaningfully, but still ruled by a few parameters, so that you can hope to combine information coming from, say, astrophysical searches and collider searches. So rather than explaining further the theory, let me just illustrate with a specific example how does it work. Indirect dark matter searches are searches where you look for the byproducts of this WIMP annihilation into standard model particles. Standard model particles can come with different type of characteristics. You can have gamma rays, you can have neutrinos, you can have cosmic rays. Why gamma rays and not anything else? Well, because if you have a bias that your particle is TeV-scale or 100 GeV-scale, the byproducts will share this energy scale, of course. Now, in the specific case of gamma rays, they are good for searching for dark matter because they retain directionality. Okay? And this is very useful in separating the signal that you are looking for from the backgrounds that might be present. And then they are relatively easy to detect. It's not like for neutrinos where you need to go to kilometer cube size detector. The flux that you expect comes from a particle physics term, which basically is the spectrum coming from each annihilation times the annihilation rate, which is the cross-section over the mass square, and an astrophysical factor, which is the square of the integrated density along the line of sight. Why square? Because you need two particles to come into contact for annihilating. Okay? So this part, given a particle physics model, you can compute. This part, you need to know how dark matter is distributed in astrophysical systems. So you go to simulations, because nowadays we are deeply in the nonlinear regime, unfortunately. So this is a typical map. It's a synthesis map of how the signal from the galactic and satellites of the Milky Way should look like if nothing else but dark matter is shining in gamma rays. Okay? You recognize a huge signal at the galactic center. This is in galactic coordinates. You have maybe a large extent, tens of degrees Milky Way halo. You have some satellites of the Milky Way, and then you have a diffuse extragalactic extragalactic spectrum, each one with some difficulty and some advantage. In particular, the galactic center here, you see it's a very, very prominent signal, but unfortunately the dark matter profile in this region is very poorly known. When I say very poorly known, means by orders of magnitude. Okay, so the intensity of this dot might change by 10 to the 4 or so. Concerning the spectrum you should search for, this is more or less under control, at least for the energies we are talking about, you know, GeV to hundreds of GeV. Why? Because basically you can compute it through the decay and fragmentation of standard model particles that we are familiar with from particle physics application. For instance, these have been obtained with Pythia. And the dominant spectrum should come from a continuum. Namely, you do not annihilate directly into photons. Remember, the dark matter does not couple directly to photons. So what you see is the photons produced by the decay of, say, pions that you produce in dark matter annihilation. But these are relatively under control once you specify your model. And then you look for signals in experiments like Fermi, which is a satellite, or earlier on Agile, which is a smaller Italian satellite, or from the ground with Cherenkov telescopes like Veritas, HESS, MAGIC. These, unfortunately, can only look for a very narrow field of view and only at higher energies, TeV-scale energies, hundreds of GeV energies, but they are very sensitive. Fermi gives you a complete picture of the sky at GeV. And what do they see? They see something which, by eye, looks very different from what I showed you before. Okay? Compare this putative signal from dark matter with what an experiment like Fermi sees. Here you clearly see a huge band of photons coming from the galaxy. And these are all extragalactic sources. A few of them are pulsars and supernova remnants in our galaxy. Okay? So the big difficulty in this game is to separate the signal you're looking for from the backgrounds that you see dominate the whole sky. Still, people are up for the challenge, and there have been many people, for instance, that have been claiming an excess of gamma rays in the GeV range coming from the galactic center, okay, in the direction of the galactic center in Fermi data. And this kind of business is going on for like 5-6 years. I stopped collecting references here and going from possible evidence to compelling case over the years. So people really got excited about that. So this is a typical morphology spectrum. This is the spectrum as a function of the distance from the galactic center that they have extracted from the data. This is the spectrum integrated over angular shape, so as a function of the energy. And these are some best fit chi-square for different channels. So the bottom line is that it seems like the data of Fermi are easily compatible in these excess over known backgrounds with the byproducts of annihilation of a particle of, say, 40 GeV annihilating into quarks or tau pairs, with a profile and morphology which is slightly steeper than what you expect from simulations, okay, for baseline choices. Now, I want to convince you that colliders can have something to say about such kind of claim, which, if you think about it, is quite remarkable, right? You point a telescope at GeV energies in the sky, you see that you see extra photons, and then you turn to LHC to tell you, is this explanation making any sense or not? Well, you can, under some assumption for these simplified models, tell something about these models. For instance, if the dark matter model that you build is such that the events that you see are not too soft, okay, this is important, then LHC experiments have sensitivity. How? Why? Because the collider bounds come from jets and missing energy and maybe associated top pair productions, so you need a lot of recoil against it, and they can exclude the case where the mediator is very high in mass. This is a typical plot that you can say. This is a plot of the dark matter coupling to the mediator. This is the mediator mass, okay? The range of parameters selected by the gamma ray data, the astrophysics, is this blue band, and everything which is about this red band is excluded. And these are different forecasts for how LHC should perform in the future. Okay, so remarkably, why? Because you have only a handful of parameters. The coupling of dark matter to the mediator, the mass of the mediator, the coupling of the mediator to the standard model, and the mass of the dark matter candidate. Well, if you have simplified models, you can make meaningful statements about the viability of some scenarios. And actually here I'm just drawing some of the diagrams through which the LHC would actually get the bounds I'm talking about. You can even use intensity frontier experiments Tomer talked about, namely experiments where you produce lots of particles and you look for tiny branching ratios in some decays. For instance, kaon physics, B physics, upsilon decay modes. And this kind of physics is complementary to the probe of LHC. Why? Because now you cannot really test scenarios where the mediator is very heavy, while in LHC you wanted something hard to recoil against. Here you are rather probing light particles, which are kinematically accessible in the phase space of the decay of these states, but with perhaps some sizable coupling. And you can get a number of constraints on these models. For instance, in this case, you have a parameter space in coupling and the mass of your particle selected by the excess coming from the the mass of the mediator, selected by the gamma ray data. Here is a regime where dark matter would be strongly self-interacting, and here it's excluded by flavor constraints for a specific choice of the pattern of coupling of the dark matter and the mediator to the standard model. You see that it cannot be true at the same time that dark matter has sizable self-interaction and at the same time annihilating into gamma rays. Also, it cannot be at all that the mediator mass is too light. It cannot be below a few GeV or so. So you see that the intensity frontier is probing a regime where maybe the mass of the mediator is light, but you have smaller coupling. LHC energy frontier is probing a regime where the mass of the mediator is maybe heavy, but you have more sizable couplings. And that's the kind of games people are yes?
So this is for the pseudoscalar?
This is for a pseudoscalar mediator.
Can you remind me what happens with the scalar?
For the scalar, actually, the main difficulty with scalar candidates is that they scatter too strongly in direct detection experiments. So usually they are excluded by direct detection searches.
If you have a small splitting, this is fine, right? I mean, you could have like
Of course. I mean, this is qualitatively true only for. No, it's not excluded. I'm saying what I'm trying to convince you is that some claim about an excess in astrophysical data, you can check at least in part of the parameter space and in a complementary way with energy experiments and intensity experiments, energy frontier experiments and intensity frontier experiments. But this is just one example. So, of course, you can cross-check astrophysical data with other astrophysical data. For instance, if dark matter annihilates at the galactic center, well, it should also annihilate everywhere else. One example being the satellites of our galaxy. These are small dwarf satellites which have been mapped and recognized in recent years. And of course, Fermi has performed analysis also of these targets. Why these are particularly appealing? Because these are extremely poor in stars and baryons, so you do not expect any astrophysical background from them, basically. So if you see any signal, it's very likely that this is coming from an exotic source. Well, unfortunately, they didn't find any signal. They put some exclusion limit, and this exclusion limit mostly exclude the regions favored from the by the galactic center interpretations in terms of dark matter. Although people are still a bit cautious because maybe the distance of some of these objects are not well known, the dark matter content is not well known. These are astrophysical 1 and 2 sigma bands, so they do not weight the same as particle physics 1. Just cutting a long story short, do other data fit this dark matter explanation? Actually, no expected associated signal has been detected right now. Okay, and there are even recent papers that seem to point out to that a likely explanation, a more likely explanation, is astrophysical in origin. But the interesting thing is that to come to this conclusion, people, as it's happening more and more often, are combining collider information, gamma ray information, antiproton information, direct detection information, and that's the kind of strategy that people are using to probe weak scale physics. So it might have been true, perhaps it still is, and the only way we could have figured it out is to combine information coming from completely different sectors. Okay? So let me just spend the last minutes to come back to put under some more discussion the traditional link that I talked about between astroparticle physics and dark matter problem and particle physics. So this is the summary of what I told you. In a sense, if the paradigm of new physics at the electroweak scale with electroweak coupling with some protective symmetry is correct, then you do expect WIMPs. Okay? The physics related to the naturalness problem, you don't have to force it to produce a WIMP candidate. It naturally comes with some WIMP candidate. So basically, you can correctly say that LHC is now probing the physics motivated by naturalness, which naturally comes with incorporated WIMPs. However, it doesn't mean that if you don't find a dark matter-like candidate at LHC, you will have excluded anything on dark matter. Okay? This is sometimes people say, okay, if there is no evidence for WIMP particles, then probably modified gravity is the correct explanation of what we see. That's a wrong inference, in the Aristotelian sense, wrong. So let me just give you an example. For astrophysical cosmology, the mass scale is completely arbitrary. For instance, TeV-scale is perfectly fine for explaining dark matter problems. And I told you that standard model neutrinos are what comes the closest to a good candidate for dark matter in the standard model, but they fail. Actually, if you make an ad hoc neutrino just heavier and with weaker interaction, weaker than weak, well, it works quite easily. Okay? It fulfills all constraints we know about. More technically, for those of you who know what I'm talking about, it's enough to add a gauge singlet to the standard model, which mixes with an active one, and you basically add the kinetic term to your theory, the Yukawa term, with this singlet state, and a Majorana mass term, and it's all fine. Okay? You just have a production of this mechanism, not through the WIMP mechanism and the thermal equilibrium in the early universe we have mentioned before, through mixing with the active neutrinos, basically by generalization of the oscillation phenomenon that has been confirmed experimentally. And then you have another free parameter, which is the mass of this state, which you tune to the KeV range to reproduce the observed abundance. Now, there is something interesting about thinking a little bit out of the box. First of all, you get an astrophysical candidate which has a completely different signature, namely, this is not protected by any symmetry. It's just long-lived because it's light. okay, and the coupling is small, but eventually it will decay. So you have a signal of a two-body final state of a neutrino and a photon, but this photon now is in the keV range. So it's an X-ray photon. It's not a gamma photon. Second thing is that you can generalize this model to add more states here, and maybe you can have a different, you can use them to explain the matter-antimatter asymmetry. In fact, if you try to do so, you select a different scale again. It's hundreds of MeV or GeV if you work in this minimal model. Again, a completely different scale than the TeV we were talking about. And what is perhaps more important, in this model, you have no physics above the electroweak scale. Okay? So apart from gravity, there is nothing that somehow violates the naive thinking about naturalness, about the fine-tuning. What is more important is that you still have another way to access, to probe these kind of models in the laboratory. However, you need different kinds of experiments, of course. So let me skip some recent hints. Basically, you can build different type of experiments, beam dump experiments, where you shoot protons against a wall, and you look for the decay products, and very, very rare processes may probe decay into these particles, or you may produce these particles and then they decay away in a decay line. And there have been, people trying to come together and discuss about alternative strategies. And in fact, even LHC and even future colliders in the energy frontier can probe part of this mixing range for heavy neutrinos or neutral leptons. So what I wanted to say is that in principle there is some big progress, big chunk of progress that has come up in the last 20 or 30 years. If you were around in the 80s, people were still discussing, is it really dark matter? Is it baryonic or non-baryonic? Is it massive neutrinos or some massive compact objects in the halo that we have been missing? Well, this is gone. We know that there is new physics beyond the standard model, and this is needed to explain the dark matter problem. Not only that, we have other evidence, like from cosmology, the matter-antimatter asymmetry. Again, this needs physics beyond the standard model. Okay. However, what I find amusing is that cosmology nowadays is a little bit like the astronomy of our ancestors. Actually, they could compute quite precisely recurring astronomical events. They knew when the solstice was, they knew the periodicity in the movements of moon and planets, but they didn't have any clue about the dynamics. Okay? And exactly the same situation is true in cosmology. We can fit the data with a handful of parameters. We can describe observation, but we don't know the physical nature of dark matter. We don't know the physical nature of dark energy. We don't know where the baryon that we observe come from. We don't even know the origin of the mass of neutrinos. Basically, in the pie chart I showed you before, we know nothing. Okay? We know the origin only of photons in that pie chart. And I try to convince you that in several models for the production of dark matter, actually there are associated signatures in different branches of physics, from collider searches at the intensity frontier to collider searches at the energy frontier to astrophysical searches in gamma rays. I didn't have time to tell you about neutrinos, cosmic rays, and so on. And this is actually where the field is right now, exploring these WIMP scenarios. And indirect dark matter, so astrophysical searches, in principle can detect dark matter even alone. In practice, this has turned out to be a very difficult enterprise. Why? Because you have lots of astrophysical signals, so it's very hard to disentangle astrophysics from new physics. You can still have some hope in finding correlated excesses in different channels, but it's very likely that if you discover dark matter of WIMP type, this will come thanks to an important progress, namely you move beyond blind searches where you look for anything anywhere, and maybe there will be an experiment like LHC that will tell you to look at some place specifically. Then indirect dark matter searches will become much more powerful. Okay, if you tell an astrophysicist working in gamma ray astronomy to look for a line at 147 GeV, that's way, way more powerful an indication than just look for an excess anywhere. Okay? And anyway, even if a signal is found in other channels, like at LHC or direct detection, to confirm that whatever you find in the lab is the same stuff that you need to explain astrophysical observation, that's a very, very challenging thing to do and needs indirect dark matter detection. Also, you want to access particle information which is not available directly at collider. For instance, the decay time of your particle or the annihilation cross-section. Maybe you want to access cosmological properties of dark matter, the power spectrum at very small scale, which is linked to the dark matter self-interaction. And currently, the best compromise somehow is to look for searches at colliders that has something to tell about searches in astrophysics, is to use simplified models that capture the bulk of the key properties of your dark matter candidate. And on the other hand, indirect dark matter detection can even go beyond the reach of LHC and can even tell you maybe some direction for laboratory experiments of the next generation. Okay, so I think this is what I wanted to say. If you are pessimistic after all this talk, remember that dark matter has already been discovered in an electromagnetic probe. Actually, in 150 years ago, astronomers had a similar problem. They could not describe very well the movement of Uranus, and some crazy guy, Adams and independently Leverrier, postulated that there must be some dark matter that gravitationally perturbed the movement of Uranus, and they tried to infer the distance and the mass of these objects. And Galle, in fact, looked at the prediction of Leverrier and found this planet that now we have discovered in full colors thanks to Voyager missions. So this is Neptune, and as you see here, French people were already playing with cartoons, mocking the British for the being late in discovering it. But actually, also modified gravity has been already discovered once, because a few years later, this claim, Leverrier found some anomalies in the movement of Mercury, and he said, haha, I found it again. There is more dark matter between the Sun and Mercury. He did the same calculation. He predicted the existence of Vulcan. Okay? And it turned out that this planet was discovered, okay, with high confidence. It was even confirmed twice, if I'm not wrong. But actually, its existence was never confirmed again. It was disproven. And the real origin for this anomaly was to be found in the modification of gravity in Einstein's general relativity. This was a successful postdiction of general relativity. So don't be surprised if discovery of dark matter will take some time. Okay, we have no theorem that guarantees that we will ever discover it, but it has happened in the past that it took lots of efforts, sometimes decades, to separate false claim from the true origin of these anomalies. And if you don't trust me on this point, I can just report that this kind of strategy is still going on. Just this year, there was the claim that maybe there is an extra planet in the solar system, so there might be some dark planet in the solar system. Let's hope that there is some dark matter to be found at LHC. Thank you.
So thanks, Pasquale, for this very nice review.
Thank you.
And question from the audience? Or curiosity about this particular field of study?
I left some suggestions for questions here and there, hoping that...
You mentioned at the very beginning,
Yes.
that something that I agree with, that it's very hard to modify, that modified gravity explains cosmology.
Yeah.
But there are claims with TeV and all kind of other scenarios that can actually change.
Yes.
Be consistent with cosmological tests.
Yes.
Do you have anything to say? I mean, do you know if they are just plain wrong or
actually, you're right. I was being a bit too rough or too too simplistic, let's say, in what my claim was. So it's true that there have been, sorry, if I find the slide maybe. So basically the point is that modified gravity does not only have to alter the rate of growth of perturbation, it has also to smoothen them out somehow. And also it has to explain these kind of clusters going through each other. So somehow it has to maybe have some non-radial feature and so on and so forth. There have been efforts, for instance, in tensorial vectorial scalar theories, trying to do that. In general, in order to do that, you need to have a significant role, for instance, of vector fields in the growth of perturbation. As far as I know, there is no single model that with current data of this class fits the data, cosmological data. That doesn't mean it's not a theorem of non-existence. To some extent, however, the problem is a bit semantic, in the sense that in all models, basically you need additional degrees of freedom. All models of modified gravity play with additional degrees of freedom. And these additional degrees of freedom behave in a certain sense, in an effective sense, like dark matter. So the difference between dark matter and modified gravity is, in a sense, is this a classical manifestation of additional fields, or is it particles that are produced? So it's a quantum fluctuation of this field that produces the phenomenology. But in practice, what matters is that you need to extend the standard model with additional fields. And in a sense, from a phenomenological point of view, dark matter is the minimal assumption because you only need a number. In all these other modified gravity, you need potentials. So you have an infinite degree of degeneracy somehow. So from a theoretical point of view, I don't think these are minimal extensions. These are much more demanding extension from a theorist's point of view. But at the bottom line, the real discriminant will be, is this just a modification which is affecting the gravitational sector practically, or do we have a chance of seeing them in any other channel? This is the only thing that matters from a phenomenological point of view. Okay?
Questions? From my point of view, the key of your presentation was this combination. You say a lot of time combination between results from the particle physics experiments and the cosmological experiments. Then you say that the time scale, okay, we cannot foresee a time scale for, let's say that dark matter exists and which shape it exists. But is this some time scale you expect to combine with some results from collider experiments and cosmological experiments to have some, let's say, a little step more of knowledge?
This is already happening.
Waiting for some results that from some experiments.
This is already happening. Every time LHC releases some new results, people go back to their astro-motivated models and update them or rule them out, and vice versa, in a sense. The point is that when do you stop this game somehow? My prediction is that it will stop when you will run out of new data. As simple as that. Once you have reached the reach of LHC, it will saturate in a decade or even less, depending on what observable you are looking at. And that's it. I mean, people will lose some interest. But there is no clear benchmark apart from the qualitative feature that is what Tomer was saying. At the end of the day, LHC was conceived to be a discovery instrument in the electroweak sector, at the electroweak scale for colored particles in particular, but hopefully for other stuff related, for instance, to the Higgs. If this paradigm that there is new physics at electroweak scale is not validated by LHC, I think theoretically WIMP scenarios will lose much of their interest, because there is nothing in cosmology and astrophysics that tells you that dark matter is electroweak scale in mass and coupling. Nothing. So you can have dark matter candidates from, micro electron volt mass to 10 to the 16 GeV mass at least, and they are perfectly fine. And you can have dark matter candidates which are on the verge of being excluded, up to dark matter candidates which are only interacting gravitationally. So unfortunately, for particle physics after the Higgs discovery, if you don't have a theoretical prior on the scale you want to look at, you know just that there is new physics, but you don't know on which scale there is. So the two directions I would say is, let's try to do our best exploiting what LHC can offer. Not only LHC, in fact, I mean LHC in a broad sense, even intensity experiments and so on. And then keep an eye open on alternative possibilities, because even if it turns out that the paradigm of new physics at the weak scale is wrong, it doesn't mean that there is no hope for collider or laboratory probes of new physics. You may have alternative strategies that are maybe as successful as traditional way has been. So we don't need to be pessimistic. I mean, for me, the real important thing is that we will very likely convince ourselves that the direction nature has chosen is not what our theorist bias was, and that's a great achievement, really great achievement. And by the way, there are other things not related to dark matter that LHC can tell us about. For instance, the interaction of the Higgs potential at zero temperature that might be important for baryogenesis, for instance. And these are things which can be probed through triple Higgs coupling or associated top production and so on and so forth. There is a long way ahead of us, but a null result now it's going to be important, honestly.
Okay, so thanks Pasquale again.